Is a very good morning, dear students. Now, in this class, we are going to continue the topic of so called polymers. So, we have learnt about the introduction of polymers in our last class. Now, in this class, we are going to learn about the very important so called plastics. So, what are these plastics? Plastics are a high molecular weight organic materials that can be molded into any desired form or any desired shape by the application of heat and pressure in the presence of a catalyst. So here the plastics were discovered and developed based on the trial and error method. And here the very important point is related to the rapid growth of these plastics has taken place only in the last 50 years. And the present time there is we sometime it is referred to as plastic age, because we are using the plastic materials in a variety of applications. And even it is the man's desire to develop plastics for engineering applications in order to replace the glass, metal, ceramic, wood and other important materials of construction. Since these plastics possess the following a very important advantages, and they have a wide variety of or wider applications. Let us go for the advantages of plastics over the other materials. So these plastics are light in its weight, and next they have very low melting point, and these plastics can be easily molded, and they possess excellent finishing. That means we can say that it is called lustrous behavior, and they possess a very good strength. We can say that the strength and toughness both are very good in this nature, in this plastics, and they possess a very good shock absorption capacity. In the case of vehicles we see that shock absorbers, and they're also having a very good corrosion resistance, and they're also chemically inert. And these plastics also have low coefficient of thermal expansion, and they possess good thermal and electrical insulating property. And the plastics are very good water resistant, and they possess good adhesiveness. So these are the advantages of the plastics, and on the other side there are some disadvantages are also there. So these plastics are non biodegradable, and therefore it will take some thousands of years for it to decompose inside the soil, and it may leads to the death of some cattle species if it consumes as like a food. So next, it has softness, and the next one, it is having the embrittlement at low temperatures, and it shows deformation under high load bearing conditions, and it shows heat resistance it shows heat resistance with a very low level, and it has a poor ductility. So, and even it has the property of combustibility, and next it shows degradation upon exposure to heat and UV radiation. Okay, these are the disadvantages of the plastics. And now we are moving on to the a very important, so the concept of classification of plastics. The classification of plastics is mainly based on the structure and type of resin used for the manufacture of plastics, and these plastics are classified into two major types: thermoplastics and thermosetting plastics. So here, what is the meaning of a resin? A resin refers to a basic binding material present in plastics which undergoes polymerization reaction during the molding process. And nowadays we are using the two terms plastic and resin as synonyms. So let us go for the thermoplastic resins and thermosetting plastics. So we have the plastics which have been classified into two types: thermoplastics and thermosetting plastics. Thermoplastics having the examples like polyethylene, polyvinyl chloride, polystyrene, and polyacrylonitrile. Whereas thermosetting plastics, they have with some examples like bakelite, polyester, urea formaldehyde resin, and epoxy resin. So let us go for the definitions of thermoplastic and the points that are related to thermoplastic. Thermoplastics are the plastics that are prepared by the addition polymerization, and these are straight chain or slightly branched polymers and various chains that are held together by weak secondary van der Waals forces of attractions. And these thermoplastics can be softened on heating, and they are hardened on final cooling, and these are generally soluble in almost all organic solvents. And you see the monomer chain that is present in this particular polyethylene polyvinyl chloride. So the one chain or one straight chain monomers is linked to the next chain by means of or through the weak secondary van der Waals forces of attractions. That's why they have the process of easy rotation of the molecules. So that's why the thermoplastics resulted in straight chain or linear chains, and these thermoplastics are formed from the very important monomers which undergoes addition polymerization mechanism. So and these are a very important type of thermoplastics or polymers which are soft, they are less brittle, and they can be recycled, reused, and they can be reclaimed from the waste. So these are the important points related to thermoplastics. And coming to the thermosetting resins or thermosetting plastics, so these are prepared by the condensation polymerization, and various polymeric chains are held together by strong covalent bonds, and these are called crosslinks. The thermosetting plastics are getting hardened on initial heating, and once they get hardened they cannot be softened again, and they are almost insoluble in all organic solvents, and these cannot be reclaimed from the waste, and they cannot be recycled and reused, and they are very hard, rigid, and they are more brittle, and these type of plastics are having the very important branched or cross-linked chains that are present in it. Next, you take the examples of these plastics of thermosetting type. They are bakelite and polyester, and the chains or the long linear chains are linked together by monomeric chains are linked together by strong covalent bonds. You see, these are the differences between thermoplastics and thermosetting resins. Hope and this table will give you sufficient data. So let us have the thermoplastics resins and thermosetting resins. So thermoplastic resins are formed by addition polymerization, and thermosetting resins are formed by condensation polymerization. The second point is thermoplastics consists of linear long chains, whereas thermosetting plastics consists of three-dimensional network structure. And the third point under thermoplastics is all the polymeric chains are held together by weak secondary van der Waals forces of attractions, and the thermosetting plastics are having the polymeric chains which are linked together by strong covalent bonds. And these thermoplastics are weak, soft, and less brittle, whereas thermosetting plastics are strong, hard, and more brittle. And coming to the fifth point, thermoplastics are softened on initial heating and they become hardened on final cooling. Whereas thermosetting plastics are once on initial heating they become softened, and on cooling they get hardened, and on further heating there will be no change in its form. That means they do not soften on further reheating. And coming to the thermoplastics, they can be remolded, whereas thermosetting plastics they cannot be remolded. And the thermoplastics have low molecular weight, whereas thermosetting plastics have high molecular weight. So the thermoplastics are soluble in almost all organic solvents, whereas thermosetting plastics are insoluble in almost all organic solvents. So coming to the next important concept, so that is types of polymerization. So the polymerization is the process of formation of a polymer from the combining of or linking of many number of small units of monomers. And here polymerization reaction is carried out by the addition or chain growth polymerization, condensation or stepwise polymerization, and third one, that is copolymerization. Let us have the first important type of polymerization, that is addition or chain growth polymerization. So it is the reaction that yields a polymer which is an exact multiple of the original monomeric molecule. The organic monomeric molecule, it consists of one or more double bonds. In the case of addition polymerization, there is no elimination of any kind of molecule. That means byproducts are not formed through this addition polymerization mechanism. Let's go for some of the examples of this addition polymerization. So we have polyethylene, which is prepared from the ethylene monomers, that is CH2 double bond CH2 ethylene, which undergoes the very important bifunctional species formation as an intermediate. So in the presence of heat, light and pressure, and by means of a catalyst, that is either benzoyl peroxide or hydrogen peroxide, the formed intermediate, that is bifunctional intermediate, which is undergoing polymerization and gives rise to the formation of polyethylene, that is CH2 single bond CH2 taken n times. This is the polyethylene. And you take one more example, that is PVC, which is prepared from the monomer vinyl chloride. And here the vinyl chloride is with a monomeric chemical structure CH2 double bond CHCl. Here this monomer vinyl chloride undergoes chemical reaction in the presence of heat, light and catalyst under some pressure. It gives rise to the formation of a bifunctional species, which is CH2 CHCl single bond. And this is the bifunctional species, which is a reactive intermediate which undergoes the polymerization in the next step and gives rise to the formation of polyvinyl chloride, and it is represented with CH2 single bond CHCl taken n times. Okay, next we have acrylonitrile is the monomer that is used and it is finally undergoes polymerization to form a polymer called polyacrylonitrile. And now you can see the preparation of PAN, so that is acrylonitrile CH2 double bond CHCN under the same conditions of heat, light and catalyst, and by applying some pressure. So the acrylonitrile monomer, which is converted into the bifunctional species, that is CH2 single bond CHCN, and on further polymerization it is going to give rise to a polymer that is called polyacrylonitrile, PAN, which is represented with the chemical formula CH2CHCN taken n times. Okay, next we are moving on to the condensation or stepwise polymerization. And here the condensation or stepwise polymerization is a reaction between simple polar groups containing monomers with the formation of a polymer through the elimination of small molecules like H2O, HCl, NH3, etc. So here the monomers are with reactive functional groups, and here there is a process of elimination of small molecules, that is HCl, H2O, NH3, etc. And coming to the examples of this condensation polymerization, or that is nylon 6,6 preparation, which is a polyamide. It is prepared by the reaction of hexamethylene diamine with adipic acid, and the condensation polymerization takes place between the two monomers and gives rise to the formation of nylon 6,6, which is a polyamide. Now you see in the chemical structure, NH2CH2 taken 6 times NH2, and it is a hexamethylene diamine, and it reacts with COOH, CH2 taken 4 COOH, and it is adipic acid, and gives rise to nylon 6,6, which is a polyamide, that is NHCH2 taken 6 times NHC double bond O, next CH2 taken 4 C double bond O taken N. So this is nylon 6,6 preparation. And the next important type of nylon, that is nylon 6, which is prepared by the very important self condensation polymerization of caprolactam. So here, without the elimination of small molecules, that is taking place. So here the elimination is not observed, so just by opening the cyclic compound, ring opening reaction, here the caprolactam which undergo polymerization to form nylon 6, and here caprolactam is represented with CO, NH, CH2, 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 which is closing its ring with CO, and gives rise to the formation of nylon 6, which is represented as C double bond O, CH2 taken 5, NH taken N times. Okay, so next, third important type of polymerization, that is copolymerization. So what is copolymerization? It is the joint polymerization in which two or more different monomeric units that can combine instantaneously and gives rise to the formation, gives rise to a copolymer, and the type of polymerization is called copolymerization. Here the formed copolymer is with high molecular weight, and the copolymerization is mainly carried out to vary the properties of the polymers such as hardness, strength, rigidity, heat resistance. Okay, next we are having some of the examples of this so-called copolymerization. So it is the preparation of Buna S or styrene butadiene rubber or SBR type of rubber. So it is prepared by the chemical reaction between butadiene and styrene, which undergoes copolymerization to give the Buna S type of rubber, or it is also known as GRS rubber. So let us go for the preparation method. Butadiene, that is CH2 double bond CH single bond CH double bond CH2, which is a butadiene, which is reacting with a styrene, that is CH2 double bond CH C6H5, and gives rise to a very important product on copolymerization to give polybutadiene co-styrene, which is CH2 CH double bond CH CH2 CH2 CH C6H5 taken n times. And we have the next important type of example for copolymerization. It is the vinyl chloride, which combines with vinyl acetate to give polyvinyl chloride, co-vinyl acetate. So let us have the equation. Vinyl chloride, that is represented as CH2 double bond CHCl plus CH2 double bond CHO C double bond O CH3, which is vinyl acetate, and they undergo the copolymerization and gives rise to the formation of polyvinyl chloride co-vinyl acetate, that is CH2 single bond CHCl single bond CH2 CHO CO CH3 as a substituent. So let us have some of the important differences present between addition polymerization and condensation polymerization. So addition or chain polymerization, which is having the monomers must have at least one double bond or triple bond, that is multiple bond. For example, ethylene, acetylene, vinyl chloride. Okay, these are the examples of the monomers consisting of double bond or triple bond. And the condensation or step polymerization is a polymerization where the monomers, they must have at least two identical or different functional groups. Example, glycol, that is CH2OH, CH2OH, CH2OH and CH2OH. Next, the second one, 6-amino hexanoic acid, which is represented as NH2 CH2 taken 5 COOH. So this is the another example. Okay, so next we are going for the second point of difference present between addition and condensation polymerization. So monomers add on to give a polymer and no other byproduct is going to be formed. And in the case of condensation polymerization, monomers condense to give a polymer and byproducts are formed like H2O, CH3OH, etc. And the third point of addition polymerization is number of monomeric units decreases steadily throughout the chemical reaction. In the case of condensation polymerization, monomers disappear at the early stage of the chemical reaction. And coming to the fourth point, the molecular weight of the polymer is an exact integral multiple of molecular weight of the monomer. And here in the condensation polymerization, molecular weight of the polymer need not to be an integral multiple of the molecular weight of monomer. Okay, next coming to the fifth point, addition polymer has high molecular weight, and coming to the condensation polymer, it has so called the polymer rises steadily throughout the chemical reaction and its molecular weight also rises steadily. So coming to the addition polymer, so it has longer reaction time, gives higher yield, but it have a little effect on molecular weight. And here in the case of condensation polymerization, there are some longer reaction times, and these longer reaction times are essential to obtain high molecular weight. Okay, so coming to the seventh point, that is addition polymerization. So these are the thermoplastics, and you see here there are examples of these addition polymers are polyethylene, PVC, Teflon, and like we have polypropylene and so on. And these condensation polymerization are with thermosetting plastics which are produced, say for example bakelite, urea, formaldehyde resins. And the eighth point of addition polymerization is they are homo chain polymers which are going to be formed during addition polymerization. On the other side, the condensation or step polymerization with the hetero chain polymers that are going to be obtained. Okay, now we have the mechanism of addition polymerization. Here the mechanism of addition polymerization can be explained with with a very important free radical, cation and anion type of reactive intermediates. Okay, we have three types of mechanisms of addition polymerization. Number one, free radical addition polymerization mechanism, carbocation addition polymerization mechanism, carboanion addition polymerization mechanism. All these types of mechanisms, they includes three major steps. Number one, initiation step. Number two, propagation step. And number three, termination step. And now let us have the first important type of polymerization mechanism of addition type, that is free radical mechanism. So in the free radical mechanism of addition polymerization, it consists of so-called initiation step. In the initiation step, so the initiator molecule which undergoes homolytic cleavage and gives rise to the formation of a pair of free radicals, and the initiator is represented as I, and it undergoes homolytic cleavage. So the bond gets equally dissociated, the bonded electrons are shifted onto the atoms equally, therefore it will produces an atom with a single electron, which is called free radical. So here there are some very important initiator molecules. So we can have those initiator molecules like free radicals obtained by homolytic dissociation at high temperature: acetyl peroxide, benzoyl peroxide, 2,2 azobis isobutyl nitrile. So these are all the examples of initiators. And coming to the very important so-called after initiation, so the formed free radical, after the formation of free radical, the formed free radical or dot, which reacts with the monomer, that is CH2 double bond CHY, and gives rise to the formation of the monomer containing free radical, that is a chain initiating species, which is represented with RCH2 CHY dot. Okay, and the formed monomer free radical will go to the propagation step. So in the propagation step, it involves the growth of the chain by initiating species by successive addition of large number of monomers. And you can see it in the chemical equation: RCH2 CHY dot plus monomer, that is n number of monomers, CH2 double bond CHY, and it gives rise to RCH2 CHY taken n CH2 CHY dot. This is a growing chain, which is a living polymer. And coming to the third and final step, that is termination. In the termination of the growing chain of the polymer, it may occur either by coupling or disproportionation reaction. Through coupling or combination chemical reaction, it involves coupling of free radical of one chain end to another free radical, forming a macromolecule, that is represented with RCH2 CHY dot plus RCH2 CHY dot. Both the free radical units, they come close and they are making up a bond to give a final termination product, that is a polymer, that is RCH2 CHY single bond CHY CH2R. So after this, we have the second important type of termination method, that is disproportionation. So in the disproportionation, the transfer of hydrogen atom takes place from one radical center to another radical center, forming unsaturated and saturated compounds, that is alkane and alkenes. So that is represented with the chemical equation: RCH2 CHY dot plus CrCH2 CHY dot gives rise to, because of the transfer of hydrogen free radical, so the formation of alkane and alkene takes place, that is represented as the products RCH double bond CHY, which is an unsaturated macromolecule which is called alkene, whereas CH2Y single bond CH2R, which is a saturated macromolecule. So the product of addition polymerization is known as a very important addition polymer. Okay, now let us go for the very important cationic polymerization and anionic polymerization, which is represented as carbocationic addition polymerization and carboanionic addition polymerization. So in the cationic polymerization, this type of polymerization takes place when electron donating groups like CH3, C6H5 are present in the monomers, and these groups will stabilize the carbocation formation. Examples, we have styrene, isobutylene, isoprene are the important so-called monomeric substances. So here the catalyst, which is an initiator, which is used to initiate the chemical reaction, or Lewis acids like AlCl3, BF3 with a co-catalyst called water. Let us start the mechanism with the initiation step. In the initiation, it involves the formation of chain initiating species, which is represented as a catalyst AlCl3 plus a co-catalyst H2O gives rise to H plus AlCl3OH minus. So the formed so-called AlCl3OH minus H plus, which reacts with a monomer, that is CH2 double bond CH6H5, which is a styrene, and it gives rise to the formation of chain initiating species, which is represented as CH3CH C6H5 plus AlCl3OH minus, which is a carbocation that is going to be formed. And during the propagation step, it includes the growth of the chain initiating species by successive addition of a large number of monomeric units, and the positive charge simultaneously shifts to the newly added monomeric units, and it will follow a very important principle called Markovnikov's rule. According to Markovnikov's rule, the positively charged addendum goes and attacks the carbon with a more number of hydrogens, and it will give the very important stable product. Now let us have propagation step with a chemical reaction. So CH3 CH6H5 plus AlCl3OH minus plus CH2 double bond CH6H5 gives rise to CH3 CH6H5 taken N CH2 CH6H5 plus AlCl3OH minus. And the next step is the termination. The termination of the growing chain involves removal of the catalyst by the addition of proton to the counter ion, that is AlCl3OH minus. And here you see CH3 CH6H5 taken N CH2 CH6H5 plus AlCl3OH minus gives rise to, so the product of this termination is CH3 CH6H5 taken N CH double bond CH6H5 plus H plus AlCl3OH minus. This is the so-called carbocation or cationic addition polymerization mechanism. After this, we have anionic polymerization. This type of polymerization takes place when electronic withdrawing groups like chloride, cyanide ions that are present in a monomer, and these groups will stabilize the carboanion formation. Say for example, vinyl chloride, styrene, acrylonitrile are the monomeric units with chloride cyanide ions. And the catalyst or initiator, which is used to initiate the chemical reaction, or Lewis bases. Say for example like NaNH2, KNH2, LiNH2. So let us go for the very important step, that is called initiation, propagation and termination. And during the course of initiation, we know that there is a very important so-called the product that is obtained with carbon with negative charge. that is the Lewis base, that is NaNH2, which will undergo the very important so called cleavage and gives rise to the formation of Na plus NH2 minus, and this NH2 minus will react with the monomer in the next step, that is CH2 double bond CHCN, and therefore it will give rise to NH2 CH2 CHCN minus. Okay, that is the initiation step. And during the second step, that is called propagation, and this involves the growth of the chain initiating species by successive addition of again large number of monomers, and the negative charge simultaneously it shifts to the newly added monomer, that is NH2 CH2 CHCN minus plus CH2 double bond CHCN gives rise to NH2 CH2 CHCN taken N CH2 CHCN minus. This is the growing chain and it is with negative charge. And coming to the final step, that is called termination. The termination of the growing chain occurs by adding of ammonia. Therefore, by adding of ammonia, the H plus ion goes and attacks the C minus, and therefore it will give the product as with the chemical reaction is here NH2 CH2 CHCN taken N CH2 CHCN minus plus HNH2, that is representation of NH3, so gives rise to NH2 CH2 CHCN taken N CH2 CHCN H plus NH2 minus, again NH2 minus is produced. And coming to the very important type of next stereospecific polymer or tacticity. Let us have the very important concept, that is called basic concept, that is called tacticity. Now what is tacticity? Means the orientation of monomeric units or functional groups in a polymer molecule can be taking place in an orderly or disorderly fashion with respect to the main chain, and this is known as tacticity. So here tacticity is defined as the orientation of the functional groups in a polymer molecule either in orderly or disorderly manner with respect to the main chain. It is known as tacticity. And here the tacticity is of three types, and it will give rise to three types of stereospecific polymers. The first one is isotactic polymer. So here in the case of isotactic polymer, if the functional groups are arranged on the same side of the main vertical carbon chain, then that type of polymer is called isotactic polymer. The term iso refers to same side. Now let us have some example for this. Say styrene is taken, that is CH2 double bond CH C6H5, which is giving you isotactic polystyrene, which is represented as CH C6H5 CH2 CH C6H5 CH2 CH C6H5 CH2 CH C6H5 CH2 and so on. This is the chain, the long chain consisting of all the same phenyl groups that are present on the same side of that particular long chain. Okay now, so next we are going to the syndiotactic polymer. What is syndiotactic polymer? Means if all the functional groups of the polymer are arranged in an alternating fashion, and that type of polymer is known as syndiotactic polymer. Say for example the styrene molecule, again we are taking and it gives rise to syndiotactic polystyrene, and you see the very important product consisting of the C6H5, that is phenyl groups, they are arranged alternative fashion, that is one phenyl group is present on the downside and other phenyl group that is present on upside, and another one is on the downside, the next one is on the upper side. Like this there is an alternative fashion of arrangement of the these functional groups. Okay, that is symbiotic arrangement of the so-called copolymer. Now let us move on to the third important category, that is called atactic polymer. Now atactic polymer is a type of polymer, and here if the functional groups are arranged randomly around the main carbon chain, that type of polymer is called atactic polymer. And you see the same chemical reaction of styrene to give rise to polystyrene, but here it is the styrene polymer is atactic polystyrene, that is with the phenyl functional groups or C6H5 groups which are arranged so in random arrangement, they are not in a specific arrangement type. And you see the first phenyl group is present downside and the second one is also present downside, but you see third and fourth are present on the upside or upside of this chain. Now that is the representation of the atactic polymer. Okay, so hope you all understood about today's class. So thank you, thanks for listening.